I already have a digit. I already have a digit.
Correct.
Yeah, so I don't need another one.
There's
I
no-
was electrical, which is
No, that's not a good idea because that's like generally dividing.
yeah.
Maybe it's just precise at this point, so it's like, okay, it's like, but then you're just like actually just listing that stuff. The homework on the other hand is like, right, x plus y equals the whole brain stuff. It's not gonna work.
I can't really, this was like
Like CT 360 homework, which is completely mindless.
correct.
Yes.
Never mind, you got
Yeah. Wait, did we have homework for that? Oh, the coding stuff. What was the homework for that? I don't remember.
CT 360 was, it's just busy work. It's the software engineering class.
I know.
But easily, I mean,
one at the same time.
yeah.
Yeah,
Like miserable. And what's worse is that it's like a group project.
Oh, yeah. I had a good team. So I'm not gonna-
Yeah.
is that chain roll in
No, my team was, well, it was pretty good. So.
This is huge. I just want to see it.
there? Which becomes chain roll. Something I was just working on. Helping all the brothers calculate. And now I'm side. I do a variable, have as much on my hands.
Why are you typesetting that in Google Docs? That's.
Because I think myself.
I see that. It's not pleasant.
You did not give yourself this one, especially when you like.
Yeah, it was conscious.
Oh,
Conscious because acknowledge it.
or you were just learning.
The truth I was like 18. It's funny. I can say 19 years now.
And even today, they make you something for your life.
Correct, that's why I'm going back 3. That's not about what I became aware. Yeah, actually, the question of the hour, W is the variable, they're just yeah, I pushed that. Because it's a constant, but it's constant, right? Yeah, I haven't pushed it. This is just my table. Because what happens is that the 2 disappears right away. Anyway. This
It's basically this.
if W is your variable to the whole right, it's product. Yeah, that's certainty or. Very. So like, there's a constant variable.
It's like that. You had an
Maybe I'm just trying.
I might be already.
5 seconds, I'm top. It's probably be like 2 days. I did this. It's rough.
Okay. We get started. So, how many of you remember what this is? People who are not raising their hands don't remember derivations, differentiation. So, this is the dark secret, unfortunately, that so either you are doing, if you just came out of high school, you would remember this. So the good thing that we did is for, depending on how long you've been in computer science, we made you forget all this stuff. Because we essentially said, computer science is all about discrete math. And you don't need to know anything about continuous math, forget all that stuff. We didn't say forget all that stuff, we are not using it. So you have to do discrete math, but you never had to redo calculus, use calculus like ever in your classes. Whereas if you are in any other engineering department in Fulton, you would still be using calculus left and right, because all other engineerings just assume continuous math basically still is important for them. Okay, so this has always been at a math level, actually, the fact that computer scientists thought they really only should care about discrete math separated them quite a bit from engineering, rest of engineering in general. Anyway, it turns out that as you basically, it turns out that you never had to use calculus for the last God knows how long you've been here. You know, if you've been here for 4 years, you have had to use calculus for 4 years in computer science. But basically, continuous optimization, which is something that we will do starting today, is all about using calculus. The only thing that actually does anything about continuous functions is calculus. Okay. The good news is at least you know the names, right, from the calculus, the old days calculus. There was limits, there was differentiation, there was integration. Which was the hard one? Integration. You understand what I'm saying? It turns out that if you just remember differentiation, and more important, if you remember this little thing called chain rule, that's pretty much all we need for understanding continuous optimization. It's not like we're not asking a whole lot from you, really. Okay, so you just have to remember what chain rule is, and mostly you kind of remember differentiation quite a bit. So in fact, I made a joke that in places like at MIT, for example, they have this thing called integration B. Like spelling B, they have integration B. Nobody ever has differentiation B. Why? That's what I'm saying. Because differentiation is boring. It's science. It's not art. If you remember from the time when you were doing integrals, there are all sorts of these special cases for doing integrals. Right? There is integration by substitution, there's integration by parts, there is integration by continuous fractions, there's integration by something else, and none of these works, and you keep looking at it and see what should I do. If you want the exact information, that's what you would exact integral. Whereas differentiation, once you understand chain rule, you're pretty much on your way. There's really nothing stopping you from differentiation point of view. And if you remember a few normal derivatives, I mean, of course, you remember the main thing is this. That's the limit of a function. Basically, differentiation derivative is the slope of the function at the point x. And if it's a multi-dimensional function, basically it is the derivative becomes a vector, because it has partial derivatives for each of the dimensions. And so derivative itself is a vector. Okay. And one of the things that you want to remember is derivative sort of tells you where the function is going in the immediate neighborhood. So that's the whole point of calculus. For those of you who might remember, I mean, up until calculus, you knew functions by their value at a given point. But calculus tells you what the differentiation tells you, for example, what limits tell you is what does the function do in the infinitesimal region around that point, right? And so that sort of tells you more interesting things about how to find out things like the minima, maxima, etc. of the functions, for example. That's one of the other things that you kind of remember. Okay, so anyway, so if we can get this, just since we did this, if we can, okay, that's fine. So what I can do is, I mean, for those of you, who know this, pretty much it's obvious, but for those of you who don't, this is like a really, really micro class on chain rule based differentiation, right? So I'll call this U, right? So then I have half U square. So half times U square, derivative of U square, that at least you should remember. Derivative of U square with respect to U, to U. But then since we call this U, then you need to differentiate U with respect to X. So what is du by dx of Wx minus C? What? W, that's it. So the answer is u times w, but then u is nothing but wx minus c. W times wx minus c is the answer. You see what I'm saying? Okay. If I wind up asking a different thing, what is w sine x minus c square? No biggie. This is the kind of thing where integration you'll get stuck. Differentiation, no problem. Right? What do? You basically say, well, this whole thing is still u, right? So half times that's u squared, so 2u times now this, we can call it v. So wv minus c. So I need to do d by dv of wv minus c. So I'm chaining now. I started calling something else u. So I really wanted the derivative with respect to x. So derivative with respect to x becomes derivative with respect to u, derivative with respect to v, derivative with respect to x. Right? And you just multiply. So this will just be wv. And then I need to d by dx of v itself. And v is sine x. Just 1 second. Do you guys remember what is the sine x derivative? Sine x is cos x, right? So I just have wv times cos x. That's the answer. Except you know what u and v are, because you just made those variables yourself. I mean, you made the substitutions. However complex this expression is, you just mindlessly apply chain rule, you'll get the derivative. And one of the nice things for you to pay attention to this is, if you have a huge big neural network, essentially you are trying to, the output is a function of 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 inputs. You see what I'm saying? Whenever you have that chain, you'll get the derivative. Why do I care about derivative? It turns out that if you ever want to find the minimum of a function or a maximum of a function, the one idea that we know that works is gradient ascent or gradient descent. Minimum for gradient descent, maximum is gradient ascent. You see what I'm saying? So the idea of what basically neural networks do is they essentially do function minimization, error function minimization by chain rule. Except since we are computer science people, we will try to do the chain rule propagation in a slightly more efficient way. And that is called back propagation. So really, math behind neural networks is chain rule. That's it. Math behind optimization, the minimum math behind optimization is just chain rule. So it's not too much to remember, honestly. Yes, there was a question.
It's a really small thing, but I was just going to say, I think that the derivative of WB minus C should have just been W, not W.
Yeah, I'm sorry, right, you're right. Okay. One other last thing, because it's really important, is what is derivative of log x?
1 over X.
You remember that? It's 1 over x. Does anybody remember why derivative of log x becomes 1 over x? It's fun trying to remember all this stuff, right? So if you remember, the one guy, derivative of e power x is what? E power x. Right? So what I'm saying is, if I say y equal to log x, then x equal to e power y. You see what I'm saying? From that, you will essentially get derivative of log x, derivative of y, dy by dx will be 1 over dx by dy, which will be 1 over x. Okay. So fine. So keep this in the back of mind, and then we'll all come back today. How many of you have actually had the time to watch that lecture that I last minute asked you guys to look at? So you guys are going to enjoy this class today. I understand that it wasn't required because I threw it in the middle of the week, but those of you who didn't, please watch it over the weekend. Okay. What I will do is I will basically I'll just go through the choices that we make. Much of that lecture is why do we make the choices we make? You know, in terms of why is it that, for example, in a minute, we'll see we're going to represent value function as a linear summation of features. Bilinear summation of features. I spent a huge amount of time talking about things like inductive biases, etc., in that lecture. So since that lecture is there, which I actually listened to this morning, and so I think it still makes sense, but it can be essentially, it'll also work well as after today's lecture, if you go back and watch the lecture over the weekend, it'll still make sense. And so that will be the only lecture you'll have to watch the weekend. Okay, but those of you who watched, if there are questions you have with respect to what I'm saying, please do feel free to ask. Okay. Anything else before I go forward into the normal lecture? Okay. So you know the story so far. I'm not going to go through it much. And you know there is the MD piece, and then we also did RL, and then we basically did model-based and model-free RL. And then last class we looked at tabular Q-learning, which is like the last thing that we looked at. Tabular. The point about the word tabular is that essentially you had a big table of Q values. Right? If you have states S1 to S100 and actions A1 to A4, then you had Q S1 A1, Q S2, S1 A2, Q S1 A3, Q S1 A4, etc. for each one of the states, for each of the actions. Each state action combination, you have a number. That's the Q value. And if you had it, you knew what the agent is supposed to do. And we talked about how we started by just guessing a Q value and iterating. Guessing a Q value and iterating. That was what Q value of Q learning is all about. So that looked like a pretty reasonable idea. Okay, so the point that we want to get into today is this is a reasonable enough idea, except it has, I have a fresh one. Hello. So in the case of, if the number of states is huge, trillions of states, gazillions of states, then this idea of actually keeping a table of numbers, yes, it works, but it's sort of very, very inefficient. It's basically not going to scale at all. And most reasonable problems you will look at will have huge state spaces, very huge state spaces in terms of the number of states that you can consider. Okay, so when you have this very large state space, there are really two different problems, both of which are important, but one is really much bigger important than the other. One is the table is too big. Right? If you want to keep the table, remember this whole reflexive agent thing that we discussed back in the beginning? So if you want to, reflexive agents are sort of tabular agents. You say if this state is this, do the action. State is this, do the action. So if you just remember it as a big lookup table, the lookup table will be huge. So there is a memory problem. There's the space problem. It's really, that's less important than the second problem, which is if you have to go to every possible state, before you know their value, it will take quite a long time for reinforcement learning methods to converge at all. Okay, we talked about, basically how to make them converge a little faster, all that stuff, but this is just too many states and it'll take like forever. So to do either of them, the other important issue is actually taking a long time is like essentially means you need more experience. You need to essentially do more things. From state 59, you need to do action A1 before you get to know what happens in state 59 when you do that action A1. And if you have like trillion states and like, K actions, then you have K trillion state action combinations. And Q learning is guaranteed to converge only if you go to every state infinitely often. By the way, this I kind of slipped through without telling you, but all those great guarantees about even random execution, random action policy will converge. All that essentially means is that asymptotically it will converge. And by the way, and also any random exploration you do should have the property that it has positive probability of picking any state for exploration. So that if you live infinitely long enough, then you will pick every state infinitely often and every state action combination infinitely often. That's when the proofs actually work out. See what I'm saying? For small things, it turns out that you'll wind up converging very fast. But for large things, you really have to go around the state space, gaining experience for a long time before you even have reasonable passable values for the Q values. Of course, you can always start with some random initializations. That's the only thing you're stuck with. So that's basically the large state space problem. So the question is, what do we do? So to put this in perspective, essentially, we are thinking of states in this atomic representation. And I go a lot on this in the lecture that people have seen, and the rest of you will see. And in the weekend, an atomic representation means the state, basically you being described by your social security number. That's it. That's an atomic representation. It's indivisible. Everybody has a different atomic. Every state, every atomic state is different. Every social security, every person has a unique social security number. What that means is if you learn something happens when you do this action in this state, number 59, you won't know anything about what happens if you do the same action in some other state like S47 or S3958. You see what I'm saying? So imagine like if somebody came while you're walking, somebody came running and then slapped you and ran away. And you asked, what's your social security number? And they gave it. Crazy people. So now what can you learn? You can learn that this guy comes again, you should go away. But do you know anything about what sort of people are likely to slap you next time around? You might say we should never generalize. A particular person slapped, only that person slapped. I probably would not, make any generalizations. Instead of this person, like an animal comes and bites you and runs away. And let's say animals also have social security numbers. The question then is, are you going to learn anything from this? Other than that, on this particular day, when I'm here, this particular social security number animal did bad things to me. That's it. I'm not going to generalize anymore. Because, what if animals get offended because you overgeneralized and their feelings are hurt? You can't do any generalization if you think in terms of atomic state representations. That's the thing that I want you to think about. In fact, one of the most interesting things is learning is not, normally when I said earlier, last class too, When people think of learning, they think about generalization. They don't think about reinforcement learning. The only kind of learning that is actually possible in atomic representations is reinforcement learning. Because you are learning for this atomic state what is likely to happen in the future. But what I'm now asking is one more step, in the sense that I figured out what happened in this state with this action. Can you somehow generalize this to say what happens if I do this action in some state that's similar to this? This is how we think in normally. The question is, what is similarity in terms of social security numbers? You clearly know that the difference between the two social security numbers is nonsensical. It's not that people give social security numbers in such a way that all Indians of a certain height will have a particular social security number. No such thing. At least the last time I checked. Right? So they're unique numbers and they really have no semantics. So you will never be able to generalize if you're an atomic representation. So what you then have to do is you have to define the state in terms of some other representation, like features, the internals of the state. Which is like a big thing, which we talked about. And it's not surprising to you. You tend to think of like a state and think in terms of its features. But up until now, I made you think in terms of atomic representations. Now I'm saying, yeah, we do need features. Because if you don't have features, we can't generalize. Okay. So in Pac-Man, for example, if you discover through experience that one particular state like this is bad, you won't know anything about what happens in this state. And that's a completely different state. You see what I'm saying? But you guys who know something about Pac-Man say, oh, those are very, very similar states. One of them is bad, the other is bad too. The way you said it's very, very similar is because you have features and you represented the states in terms of features. So if you have these kinds of feature-based representations, then basically the idea that we'll have in those cases is, suppose in the Pac-Man, by the way, you will do this in your project. You will do Q-learning agent with features. Okay. So if you are doing some features, some reasonable features that you may have thought about for this kind of a problem would be things like distance to the closest coast, distance to the closest dot, number of goes, is the Pac-Man in a tunnel, etc., etc. So you can ask the values of these features are a partial description of the state. Right? For example, if somebody did slap you and run away, and then you go to the police station and say somebody slapped me and ran away, I want you to do something about it, they'll start asking, how tall is this person? Do they have long hair or short hair? Did they take 471? They don't ask that question. I don't know why. Actually, the interesting point is that all of those are features, but some features are irrelevant as to whether or not you slap. Although I think some guy who saw that they have to know multivariable differential calculus to do the rest of the thing, he or she probably slapped a few people on the way to the class. Okay, so it would have been a relevant variable then. But in general, my point is, they'll ask you to describe people in terms of features. And one long thing that I do in that lecture that people have watched is, that's how many societal biases come. So these differences between representation is a bias, is an inductive bias. If you decide to represent people by the color of their face, you understand what I'm saying? It's one of the features. Then there may well be a correlation between that feature and some other decision variable. And correlation doesn't mean causation, but since we don't often, most normal agents will go with correlation until they get a causal theory. That's how all these crazy societal biases come, but we won't talk about it right now here. We'll just say, no, these are the These are the features. I'm going to represent these features. So this, let's say this is F1, F2, etc., Fk. To make life simple, we'll assume all of these features are real numbers. Okay. So then a state really is a vector of features, a vector of these feature numbers. The nice thing is now I can start talking about two similar states in terms of they have very close feature representation. You understand? Okay. Let me just do one thing in case somebody is. Yeah, okay, that's fine. Okay. So I have these features, right? And then I'm going to use this. Then the question then is, I want to represent, I want to do TD learning right now, essentially. I want to do TD learning. I want to represent the value of a state, which used to be V of S. In TD learning, that's what you compute, right? You guys remember TD learning, temporal difference learning, you compute V. In Q learning, you compute Q. Both are real numbers anyway. We'll just do TD learning upfront right now. So the value of a state will be V of S before, right? Now it is a function of these features in some sense, because a state is really not a unique source accurate number of the state. It is a bunch of features. And if two states have the same features, then they're basically, from your perspective, they're identical. Do you understand what I'm saying? So in this class, how are you represented in this class? Well, for your grades. Your grades, typically you'll be represented in terms of your homework value, homework 1 value, homework 2 value, blah, 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 project 1 value, project 2 value, blah, 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 midterm value, midterm, and the final value. And I combine them into some homework feature, the project feature, and the test feature. Right? And if there are two students who basically have the same cumulative homework grade, project grade, test grade, first, of course, I'll say, why the heck are they having the same exact numbers? Maybe they're copying, etc. But even if they're not copying, right? I would just say basically those two students are equivalent as far as this class is concerned. Does that mean they are the same student? Of course not. They're two different students with two different student IDs, two different posting IDs, two different social security numbers and all that stuff. But from my perspective, those are the only things that matter. As to why this representation is a biased representation is when at the end of each course, I'll know people who have understood the material and might actually go on to do research in the area. And I'll also know people who are at the A+ level in terms of their totals, but probably just know what happened in this class and have no deeper understanding. Unfortunately, the grades are not, in fact, I used to have a colleague, Jennifer Alga-Drapkin, who said, she was a professor here, and she said, her sad story of her life is that she would understand material of every class deeply exactly 1 week after the final. Just 1 week after the final. Think about it. That's amazing. There are bozos in this world who don't understand what happened in a particular course, even at the end of their lives. This lady was understanding it 1 week after the final. But because the representation was basically what are your numbers by that particular date, she wouldn't get very high GPA. You see what I'm saying? That's when people will ask me saying, oh, can you add some participation credits? I'm not looking at my laptop during the time when you're talking credits, etc. And there was credits. All the laptop people are basically gone as far as the grades are concerned, right? So there are all these other fudge factor features which I might make up, but if I'm just making these are the features, then it will actually put two students who are completely different in the true objective understanding of AI at the same level. That's the representational bias. It could be even worse of a representational bias if I just said there's an entire semester of no exams, fun, fun, fun. You don't have to show up. I won't bug you for showing up, etc. End of the semester, there would be a Nobel Prize quality exam. Do you see what I'm saying? And then based on that, we'll give you grades. You see what I'm saying? That's a feature too. There's just one feature for each person, which is, did they do well at the end, the end of the semester exam, which was extremely hard, and there was no preparation done, etc., etc. There was no homework, etc. That you would say is even more biased, quote unquote. But every representation is a kind of a bias, an inductive bias. Okay. And one of the other things I mentioned is we make representations in terms of the task at hand. Like, for example, even though your personality and your, as you as a person, your sense of humor is probably an extremely important characteristic of you as a person. But I don't have a column for the student's sense of humor in my class. If you're dating, yeah, my God, that's like the most important column. Nobody seems to care about your homework grade in that. So the representations that you will wind up getting depend on the end decisions that you're going to do. So one of the things, of course, is that, so anyway, instead of doing a large table to represent VRQ, we are going to represent their values as some function of their features. Some function of their features. And then we'll just learn the functions. So imagine there is a function called V star in terms of features F1 to Fk. Function in the way you know math functions. Like it could be sine of F1 plus 1 by cos of F1, F2 minus log of F3 square, blah, blah, blah. That is a function. Suppose I pick this function up out of the air and say, this is actually V star. It turns out that's the V star, let's say. Then I have solved all my problems. The analytical functions take very little space. Right? I mean, if you have an equation y equal to mx plus c, you wanted to store it in a tabular form, saying for x value this is the y value, for x value this is the y value. How big will the table be? Infinitely large. But if you remember it this way, you just have to remember two numbers, m and c. That's it. Huge compression. That's why we learn functions. The other thing is, instead of actually looking at all the values of the different states as if they are disconnected, now we are essentially going to be trying to guess the values of these parameters, which are these weights for features. I'll get back to that in a minute. And when I do that, when I change the weight for a feature, it is a global change. And as I say in the lecture that you've seen, suppose one of you people come to my class, office at the end of the semester and say, really, Rao, I really did well on the homeworks. The project was a problem. And you said, these are the weights for the homework projects and exams. Then we just have some kind of an agreement that for me, you increase the weight for the homework and reduce the weight for the project. Won't you ask for that? Of course you'll ask. Whichever you do well, that's the one that you should get 100% of the weight. The rest should be 0. And Lord help those people who do badly in everything. They don't know what to put their weight on. Right? You do that. But then if I agree with you, then in essence, I've changed the weight for the entire class, unless I start having a separate collusion, like you give me money under the table, which I'm told I'm not supposed to take, apparently. Okay. So if I agree with you and I change your weightage, then I've changed it to everybody. then it may well be that your relative grade is probably just as sucky as before. I don't know. Do you understand what I'm saying? But this is a good thing, because in trying to change your effective grade, computation, I've changed everybody's. So it's like one small change has global implications. You can see it as a bug from your perspective. You wanted all the other people to keep their grades and your grade to improve. That's what you wanted. No, even better, their grades go down, your grade go up, even better. But what I'm doing is everybody's grade. You see what I'm saying? Okay. And so it's actually that part. So if you wind up changing, if you wind up learning the weights during this value function computation, then every time the weight changes, all the states values have effectively changed, because you're changing the function by which the value is being computed in one fell swoop. This never happens in tabular setting, where if you change the v value of state 1500, 1501 doesn't change, 1502 doesn't change, nobody changes. Only that guy changes. You see what I'm saying? Yeah.
So I had a question about features. Do you have a special or separate classification for observability and determinism of features for an agent?
For now, let's talk about deterministic features. There's an interesting question as to whether the features can actually be exactly measured, which will sort of be connected to whether the state is fully observable or partially observable. In general, when we say states are partially observable, that means certain features are not observable. Yes.
When we say like learn parameters from experience, is that something you have to tell and put it into our thing, or is it something
I'm
that?
sorry, can I say?
Like on the slide it says learn parameters from experience. Is that something we put in ourselves when we make our function, or can like the program make it find parameters?
So learn parameters. This one. This we are going to learn. I'm going to tell you how to learn the parameters. But there's a different question. You could have asked, who gave me the features? And for now, basically, I'm saying here, I gave you the features. Those are not being learned. Again, there's a huge point about this in the lecture that those of you who watched, which is when I give the features, I, the human who has some understanding of this game, is giving the features. So any representational biases are really because of my biases. At the same time, more likely than not, I will probably give you features that are actually relevant. In fact, I make this whole point that there is no feature about the color of Pac-Man, which is like to me the most interesting part of Pac-Man. I mean, I hate video games. I mean, I get addicted to lots and lots of things in life, but never to video games somehow. Okay. So I never played this, but the thing that I liked about Pac-Man is it's nice and yellow, right? I mean, feature, there should be at least one feature about the color of the Pac-Man. I didn't give it to you because if I gave it, I would have given it to you. These features are given by people who know actually how the game works, and they realize the color of the Pac-Man has nothing to do with the game. Do you see what I'm saying? And I'm getting you. One important thing is, this is one of the things that's like mind-blowing. What we'll wind up doing is we'll give you features, and with respect to the features, we fit to the value function. It's like function fitting, which the closest you have done about function fitting in your lives is straight line fitting through data, where the function is a straight line. In fact, more or less, that's what we'll do first. Okay. Now, the interesting thing is that if you keep increasing the features, at some point of time, you will find some random correlation between some of these features and what you're trying to predict. And that correlation would be a spurious correlation in the sense it just happened in this particular data. But you can't tell whether it's a spurious correlation or whether it's always going to happen. So when people give features, they will remove most irrelevant features. On the other hand, if you do the same thing with deep RL, deep reinforcement learning, the idea there is that the system is going to look at this in terms of pixels. Pixels, the way you're looking at it. Right? I mean, at one level, you're looking at this in terms of pixels. It's just that very effortlessly you're converting pixels into objects. And you're thinking in terms of objects. We look at the world in terms of pixels and signals. We think about the world in terms of objects and relations. It's extremely important for us to understand that. So when people give you features, they'll give you in terms of object level features. If the system is trying to pick features from pixels, it can pick any arbitrary pixel configuration and their intensities as a reasonable feature. And it might well be able to find the right fit with respect to these arbitrary quote unquote superpixels that it's finding and the decision it needs to make. And then if you ask, why did you make this? That's what I learned. And remember the ostrich school bus example? That's the one that happened there. Right? It's damn sure that the school bus was an ostrich. You ask why? It will show some number of pixels, all over the place and say, hey, that's it. And you say, what am I supposed to do with this? Because you don't see the world that way. So if you also learn, in deep RL, you also learn features. That means you are learning representations. And learning representations is a very reasonable thing to do for tacit domains where you don't have much of features to begin with. It may be pretty unintuitive for people in the loop in trying to make sense of what the AI system is doing if they can't understand what those features are. You see what I'm saying? Which is where the whole deal about interpretability and explainability of AI systems has become a big issue now. If you learn your own representations, why would it be likely that the representations that AI system learned would actually be the same representations that we have evolved to use? And if you ever think if you're not sure why it is not natural for us to have the same representation, for the AI system to have the same representation as we do, remember the school bus ostrich. That system does very, very, very good classification of most images that you do, except it does this stupid classification that you will never do. So if you just go by the end answer, you are sort of agreeing most of the time. But when it fails, you have no idea. And by the way, this representation, learning representation, I mentioned that, in fact, the deep learning people really talk of themselves as representation learning people. And so the main conference in deep learning is ICLAIR, which is International Conference on Learning Representations. I'm not saying you should do it. I'm just saying if you do it, then don't expect that the representations you learn would make sense to the humans. And when the machines take over and we just sit on like an easy chair and take it easy, it doesn't matter what they do, how they're thinking. If on the other hand, in the middle time you want to talk to them, it matters that you have a sense of what they're actually doing, that you can trust their decisions. And trusting the decisions is not just based on they were very right lots and lots of time, because that's what ImageNet classifiers were, right most of the time, except these bad examples. Okay. So we are going to do this function approximation, and yeah, this unfortunately you can't see this. So what is doing is okay, no, actually, right. So what this thing went away. So what we are going to basically say is V of S is represented as. Okay, actually, let me see if I can just go into. Okay, let's write it. What I'm planning to do is I'm going to start writing V of S. So I'll assume that I have features F1 to Fk. We'll assume these are real numbers. And V of S is represented as some function of F1 to Fk. It's a multi-dimensional function of F1 to Fk. Now, if I say which function, there's infinite number of functions. You see what I'm saying? Infinite number of functions. So when in doubt, what do? We look for a linear function as the first bit. That's what we do, right? I mean, if I show you some data and say, what curve is this? I say, oh, a line, all right. You'll always find a line. You see what I'm saying? Which is like the best line in the sense that's the line that is minimizing some error. You know, that is a line such that anything off the line, the distance of any of these points off the line, if you square them and add them, that's minimized. That's what is called this sort of line. So did you guys do this in grade school, in high school? Least squares fitting of straight lines to data. That's what you're going to do. Except you did this for one dimension. I'm going to do it for k dimensions. More than 3 dimensions, I can't show pictures. So it's just basically we have to hope that the math works. So one of the funny things is multidimensional calculus is useful mostly before here in physics. Physics is child's play. It's 3 dimensions. If Einstein comes along, he'll say 4 maybe. The string theory people say 18 dimensions. I can make up 100 dimensions, 100 features, just handmade features for this. And you allow them to learn features by pixels, they can learn millions of features. Maybe mostly useless, but they'll learn millions of features. So you're talking about million dimensional line fitting. And what we do is we'll say, the same math will work, which actually it does. The math works, your intuitions don't. The math works, but the intuitions don't. Here is a great example before I go off, which is if I have an apple, I mean, those of you who saw the lecture, you know this. If you have an apple, you peel the apple, right? And assume that it is a spherical apple, and you epsilon peel. There's still apple left to eat, right? Right. So what is the volume of the apple that is left? The ratio of the volume of the apple that is left to the original apple is r minus epsilon cube by r cube. If it's a 2-dimensional apple, it's r minus epsilon square by r square. So now I give you an n-dimensional apple, 10,000 dimensional apple. And I bought on Amazon a nice 10,000 dimensional apple peeler. And you visualizing in your mind, you peeled an epsilon thickness. How much apple is left? 0. Close to 0. Why? Because it's r minus epsilon by r power n, where n is 10,000. R minus epsilon by r would be a number less than 1. And if there's one thing you know about math, if you take a number which is less than 1 and you multiply it by itself many times, it will go close to 0. This is why we were using the geometric series business, right? So all n-dimensional apples are all peel, no core. Three-dimensional apples are all four very little peels, unless granny apples, which seem to have very thick peel. I don't like that. You see what I'm saying? So the point is that your intuitions about n dimensions don't actually hold most of the time. We will talk about it a lot, but the math actually works. So we'll act as if the math is working and we'll do some calculations. So we say V of S, we'll say is W1 F1 plus W2 F2 plus W3 F3 plus blah, blah, blah. In fact, I can also say W0 plus W1 F1, W2 F2, W3 F3, blah, 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 WK Fk. That's my function. That's my linear function. Notice that instead of looking for any possible function, including logs, sines, and every possible thing, I just said, I only care about linear functions. I reduce the number of functions I have to search now tremendously. How many are left right now? This basically is a class of functions, right? Basically. So for every different values of Wi, there will be a different function. So how many are there? Infinity. So there was a big infinity of all functions. We spent a lot of time. We made it into a smaller infinity of just the line functions. Let's do a star search to find the best function. We'll get screwed. Why? Because it's a continuous space. It's not discrete space, it's continuous space. There are infinite number of lines corresponding to every real value vector W0 to WK. So I need to find among all these vectors, the vector, the weight vector that has some good properties. Now, what is the good properties? The properties are, suppose I have the actual table, which says V of S1, V of S2, V of S3, blah, 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 and then says this is 0.7, this is 1.9, this is 1.5, blah, blah, blah. So I have some values in front of me. So for each of these states, I also know their feature values. Right? If it's if it's a Pac-Man, then I'll know how many ghosts are there, how far is the nearest dot, and all that stuff. So I will initialize. So for any particular weights, let's say I initialize the weights, let's say for some numbers. For any particular weights, if I plug the feature values and the weights, I will get the number that is actually predicted by this. We'll call this V, we call this hats, okay? Predict by the V hat, which is the estimated value according to the features. You see what I'm saying? So maybe, I mean, if they're all same as 0.7, 1.9, 1.5, etc., then you are like the luckiest person. The first pick of weight values wound up being correctly fitting the data. If not, you essentially have, let's say this is 0.7, but your estimate says this is 0.9. This is 1.9, your estimate says this is -3. This is 1.5, your estimate says 3.7, blah, blah, blah. So what I'm trying to do is to set weights such that the difference, each cell-wise difference, such are minimized. And the difference can be either negative or positive. So I can't just add up the differences because the positive will cancel negative. That much you agree. So the first thing we would like to do is actually absolute value of the differences and add them up. We won't do that. Why? Because we are about to use derivatives. And if there's one thing derivatives don't like, they don't like this kind of functions. This is mod x. Remember this? Is this a continuous function, by the way? How many people think it's a continuous function? How many think it's not a continuous function? Okay, the majority is right. And those of you who think this is not a continuous function, make sure that you understand calculus again. It's a continuous function, all right. The reason it doesn't have a derivative is the left side limit of the derivative is different from the right side limit of the derivative. Because if you're coming from this side, you think the slope is this. If you're coming from this side, you think the slope is this. The limit exists only when the left side and right side. This is the stuff that I don't understand how calculus is not made interesting in high school. Unfortunately, in some sense, it should be taught again calculus. When you have sense of how life works, and then it makes lots and lots of sense. All of these things make sense. So left limit is different from right limit. That's why absolute values are no good. Because it's not derivable, it's not differentiable. On the other hand, x square looks like that. So if I take the errors, square them, add them up, and then look for the w's that are going to minimize that sum, I win. You guys get what I'm saying? Okay, so that's what I'm going to do. What I'm going to do essentially is, I'll just say error is, for reasons which make no sense whatsoever, other than the fact that you're already primed to this, will define the error as half of what v hat predicts minus what the actual value in the table is for that state. Square it. Okay, so I should just say this is SI. You see what I'm saying? Okay. Normally, we should really be doing this over the sum of all states, but for now, actually look at just one state. That one state whose error, whose value you try to predict. Because this is actually a useful thing, because if you think of what happens in TD learning has values everywhere. So it actually has a value function with some weights. It just saw a new target. It needs to nudge the current state's value to be closer to that target. And so it's going to change. Previously, we would just change what is in the cell for this state. Instead, now we change the function. Again, this is where that example about the student coming and saying, just give me a better grade by changing the weight for my homeworks to be higher than my projects. If they just said, give me a better grade, it's simpler because I'll just give them a better grade and nobody will know. Well, they will know, but that's at least local change. If they say change the weights, then when I change the weights for them, and I'm not saying only these people will do that, but I mean, when they change the weights because they came, everybody's function has changed now because the same function is being used everywhere. Right? And so in the normal value learning, you just change the cell value. In the function approximation value learning, you change the function's parameters. The parameters for this function are these WIs. You see what I'm saying? Because this is nothing but W0 plus W1, F1 of SI plus W2, F2 of SI plus blah, 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 WK, Fk of SI. And this is a number. And this number minus this number I squared. I'm trying to minimize that. Okay. Now, when I need to minimize this, it turns out the value depends on the W's. So the things that I get to change are W's. Okay. So essentially this error function, right? You should really see it as a function in k-dimensional space, where the dimensions are f1, f2, f3, f4, etc. I'm sorry, weights. The k-dimensional space where the dimensions are weights, w1, w2, etc., wk. And in this space, the error becomes minimum somewhere. That corresponds to a k-dimensional point, w1 to wk. That's the one I want. That's nothing but saying, I have a function. Can you find the minimum point for the function for one dimension? How do you do that? Calculus, equate the derivative, equate it to 0. If you can actually solve the derivative equal to 0 equation, you will know the exact value. If you can't, then you can do iteratively come to the place where the derivative becomes equal to 0. What you do is you start from the value of the function and take a step opposite. If you're going for the minimum, take a step opposite to the direction of the derivative. A small step. How small? Fudge factor. We'll call it a learning rate. Again, this learning rate is also called alpha, but it's different alpha from the other alpha that we saw in the Q learning, tabular Q learning. This learning rate is essentially take a small step in the direction against the direction of the derivative. If you do this and if you do it repeatedly, you will get to the 0 value. I mean, you will get to the point where the function becomes minimum. And at that point, you just read off the x value, and that's your minimum x. And in the lecture, and maybe I'll say it later again, I basically point out that the alpha being a fudge factor is only needed because we are not doing the true Newton-Raphson method, which essentially would require you to also compute f dash and f double dash. That means derivative and double derivative, which for one-dimensional functions, single variable functions, f dash is a scalar, f double dash is a scalar. Both of them are scalar numbers. But an n-dimensional function, a gradient is an n-length vector. And the double derivative is an n-square matrix. You can see this already for 2, right? Because it's like dou square x by dou square f by dou x square, dou x, dou y by dou f. Right? These are the partial derivatives. So you can essentially do once with x, once with y, or both times with x, or once with y and then x. And x with, and the order doesn't matter for the partial derivatives. So for 2-dimensional one, it will be a 2 by 2 matrix. For n-dimensional one, it will be an n-square matrix called Hessian. People don't want to deal with Hessians, not just because Hessians originally were from Germany, but Hessians are basically painful. It's like n-square matrix. So it turns out people find all sorts of ways of figuring out how to change the alpha value slowly, such that you will still get to the, that's the gradient. Okay, so let's complete this part for now. And so all I need to do, all I need to do then is that for this particular case, right, the Wi will be updated by Wi minus alpha times dou error by dou Wi. This is from calculus. If it is a single variable function, you would have understood this is basically making a step in the direction opposite to the derivative. I'm doing it for each wi. Right? So I just need to give you a little nudge, how to do this little nudge for wi. And this is wi previously is a number. Remember, at any given point, you would have some weights. Just as before, you used to have the value function for every cell was initialized. Now you don't initialize the value function. You just initialize k weights. And based on those k weights, they are currently guessing some values for every state. And you know what the true values for those states are. And then you're trying to get closer. In this particular case, you're doing it only with respect to one sample. Just one sample that you've seen, you want to change the weights to be closer to that sample. Okay. So this basically all I need to do is this. This alpha is a fudge factor. I will call it 0.1. This number, you know, I just need this number. Right? And that number is basically what you did in the beginning of the class. Right? Except in the single dimensions. Now I'm just going to do it for the double dimension, multi-dimensions. So remember that I need dou by dou wi of half of v hat s minus vs squared. That's what I need to compute. And by the way, why half? Because you call it this, think of this as u, let's say, then it will be 2 times u. And you cancel 2 and 2, and you feel extremely good. That's the same, that's the only reason. If you minimize the half the error, then you minimize the error. There's some other reasons, but really the best reason is half because 2 gets cancelled. Okay, and it doesn't really matter. If you don't have half, it still will be working fine. Okay, and to u, and then basically I need to differentiate u. That is dou u by dou wi. What is u? U is nothing but w0 plus w1 f1 plus w2 f2 blah blah wk fk. That is this part minus vs, which is a number. I'm trying to do dou by dou wi of this. Right? Yes.
Should all of them be x and y as well?
Yes. Yeah.
Why are we minimizing like the sum of the squares? It seems like this, like, why would we minimize the sum of the squares as opposed to minimizing just the difference?
As I said, difference won't work. Difference will cancel out. You can minimize the absolute value, sum of absolute values, but that doesn't have good analytic properties. And so you minimize sum of squares. One thing that you will see in general, and again, I mentioned this in this lecture, it looks like everything has been mentioned in the lecture and I'm just doing some song and dance here, is that there is a connection between what math allows you to do and what you want to do. Oftentimes, you really want to do something else, but math only allows this, so you do that instead. I really wanted to minimize the absolute sum of the errors, but it's too hard to do it given the math that I have. It's much simpler to minimize the square error. And it works mostly, although it's not exactly the same, because after all, you do know the, so absolute error is like this, right? Okay. The other one, x squared, will be actually, you have to do it right. It would be, in the beginning, it will be lower, and then go like this. That is x squared. Right? Because for points less than 1, x squared will be less than x. And then points more than 1, x square will become much bigger. Right?
This introduce like bias, like your
Yeah. All sorts of biases. But let's do this first and then listen to that other lecture too. Everything is basically what we are doing here is hugely ad hoc. But life is hugely ad hoc. We make random generalizations and live. You cannot live without generalization. You cannot live with generalization. If you don't do generalization, you would have, if your ancestors didn't do generalization, they would have been eaten by the tigers. We won't have this class. Right? If on the other hand, if you're doing generalizations without realizing that these are ad hoc generalizations, you would be a bad human being. You would say, the guy who hit me looked like Rao, so people who look like Rao are the hitting types. That looks like a good thing, that's what you did when you saw the tiger and ran away. But then Karthik and Siddhant will be very unhappy, saying Rao is the bad guy. We are pretty nice people. We don't hit people. You understand what I'm saying? Okay, so this is basically, if you do this derivative, what will happen? It will just make all of these will become 0, except Wi, Fi, Si. That's the only thing that will be non-zero. And the dou by dou Wi of this will be just Fi, Si. Right? So I have my partial derivative because that is basically nothing but u times Fi, Si. That's the partial derivative. Where u itself is this, v hat Si minus v Si. That's a number. And I go put that number into this, multiplied by alpha, subtract it from W, that nudges the W in the right direction a little bit. And I then pick one more state and do this update. If you keep doing this, in essence, it turns out that every time you change the W to make one state happy, all other states got affected, for better or worse. But it takes, in general, if it works, it actually takes much fewer iterations for RL to converge. And the thing, of course, in doing this is that in trying to get to, just a second, trying to get to just something like generalization of RL, we fell headlong into calculus. You need to understand this stuff. It's not that hard, but you need to understand this stuff. I could have taught you all this because the whole of pandemic, I was teaching my dad calculus. And you'll notice that I was teaching him enough that we could have almost written an iClear paper, because all you need to know is function minimization, and then you are in business for as far as neural networks are concerned. Which is part of the reason why I was remembering that if you do x square on top of mod x, then you have to remember that x square will be below mod x in the -1 + 1 region and above afterwards. If I didn't tell you, you would have just probably, if I didn't remember that, I would have just written this way. That's not correct. Turns out, because x square is actually less than x for -1 to +1. So you need to get the calculus back into your heads. You need to make sure that you understand at least this stuff. By the way, you should be able to do this. This is a nice application of chain rule. And it's also a sigmoid function, which essentially, one last thing that I want to point out is that, I mean, this is a great thing, is if you are thinking that B of S is W1, F1 plus W2, F2, blah, 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 I can say F1, F2, K, W1, W2, WK, yes. neural network. Small one, but there it is. That's what neural networks do. F's are the inputs. They throw the inputs. They see what the output says with respect to the current weights. They see what the output should be. Take the difference. Define a loss function. In our case, we define the loss function as a square error. And then essentially compute, update the weights. Here we did that from scratch. In neural networks, we just do this as a backward prop. And in fact, bozos of the world don't even need to know calculus because they'll say PyTorch will do it, which it does. I mean, the point is that it's actually interesting to know that the progress of civilization can be measured by how many bozos can still survive. Many of us in the old days would have been eaten by tigers because we don't have, enough skills to survive. But now with all the different people doing different things, you can live your entire life without knowing much of calculus. If you're outside of engineering, no problem. What's interesting is even within engineering, even within computer science, even within Google, you don't need to know calculus because PyTorch does it. And this is what, when people do this, they are doing neural networks. I get lots and lots of mails from the undergrads. No undergrad ever says, I've done value iteration on MDP, I want to do more. Zero chance. They've all done GANs. They've all done multi-layer neural networks. Wow, that's very smart. Well, of course, PyTorch allows call GAN. And you're done. So this is actually a perceptron. And then if I basically make these multiple layers such that F's are connected in the middle and then they are connected again, it becomes a multi-layer perceptron. Then the features will then lead to intermediate layer features, which then lead to the end value. It will be multi-layer neural networks. Turns out, chain rule still works. And the backpropagation just mechanizes that whole thing. So in some sense, you send the forward message, F times W, send it off, and then the backward message is the partial derivatives.